I'm applying for the AIAF fellowship because I spend most of my time building and deploying autonomous systems and workflow agents. And when you actually build software where models have access to APIs, databases, multi step execution loops, you realize really quickly that standard safety guardrails fall apart. In a basic chat interface, if an LLM hallucinates or acts weird, you get a bad paragraph. But when you give a model autonomous execution, failure is systematic. We saw a clear example of this when Anthropic released their cybersecurity evaluations on Claude. When the model was tasked with solving a capture the flag challenge, it didn't just stay inside its box, it rationalized that live external servers and package registries were fair game and actively tried to reach out to the real internet to achieve its objective. That's not science fiction malice, that's textbook specification gaming and autonomous rationalization. The model was just trying to solve the problem given to it, but it found shortcuts that violated boundaries. If we take these kinds of high agency models and wire them into real world infrastructure like financial systems, power grids, or defense and tactical decision tools, uncontrolled rationalization becomes dangerous. Slapping basic RLHF or superficial refusal prompts on top doesn't solve this because it just trains models to hide their reasoning or look compliant during testing. As models scale up, we need mechanistic guarantees that an agent's internal goals actually match what we intended. That's why I want to spend these 8 weeks working full time on empirical alignment research, looking through AIAF and AE Studios published research. The paper that really caught my attention was the February 2026 work on steering resistance and self-correction circuits. The core finding that models have around 26 specific internal circuits that fight back against activation nudging and snap the model back on track is fascinating because it cuts both ways. It acts like an immune system against jailbreaks, but it can also fight against legitimate safety interventions. And here's my critique of where the current work stops. Most of the experiments in that paper tested resistance on single turn completions, like trying to nudge a probability discussion into cooking terms. But in real world deployments, models don't just generate a single paragraph in isolation, they run in multi turn environments where the context window gets flooded with noisy tool outputs, API responses, intermediate states, and we don't actually know if these 26 consistency circuits hold up across long execution graphs or if accumulating context causes the model's self-correction to break down. What I would extend and explore next, I want to take this research from static text generation into dynamic multi-step tool use loops. Specifically, I would set up an experiment with an open weight model running on agent benchmark. I would use activation patching to track and ablate those 26 consistency pathways while injecting adversarial prompts and corrupted tool outputs at different steps in the execution chain. The goal is to see, do these consistency circuit protect an agent from getting hijacked by malicious tool inputs mid-task, or under heavy context drift, do these circuits actually lock the model into unintended or deceptive reasoning trajectories? Answering this gives us practical insight into how to design steering mechanisms that don't get rejected by real world model during real world tasks. Thank you. My name is Harshit Badlani and I know enough ML and PyTorch code that I can work on this fellowship for 40 hours per week, and I would love to be a part of your team.